about this morning. I had to move to the hospital. I'm coming live from a labor and delivery room in the hospital today. Uh, we're kind of just waiting for things to happen, so I've got a little bit of time. I thought I would actually record the lecture that I was going to give this morning. I'll probably post it to YouTube. You can watch it in your spare time. One kind of nice thing about recording is you can probably speed me up a little bit if you want to get through it. I think you have an option down here in YouTube to speed me up maybe to 1.5x. Maybe could do that here to help out. I've prepared a little bit already. I'm going to go over to the writing pad and we'll just get right to it. Okay, so I'm now sharing my screen and we'll review a little bit last time what we discussed. And then we'll get into new material. Okay, so last time we were discussing distributed loads, and a distributed load is basically a force that acts over some length or some area. It's going to be a length in 2D and an area in 3D. So one of the classic examples that I think we kind of see in Wisconsin quite a bit is snow on a rooftop. So snow on a rooftop, you can sort of see in this image here, there's a lot of weight that is acting on this particular rooftop here. And you want to sort of model that not as a singular point load, but as a sort of line load acting over the rooftop. And so over here on the right, we show a bit of a model of what that might look like if you're looking at, let's say, one portion or segment of the rooftop, where you have, okay, like this would be kind of the roof here. And then in blue here, you have this trapezoidal figure, which is meant to represent sort of like the distributed load or the snow that's sort of acting to push down on the top of the roof. And kind of the point of this lecture is trying to discuss how to do the analysis of these distributed loads, where we're transitioning them or transforming them from this distributed case into a singular point load. Here in this image, it's represented by the capital letter R, that we can then use our tools that we've talking about for the first 10 weeks of the course to analyze free body diagrams of this and figure out sort of what loads the roof is experiencing. So these distributed loads are defined by loading functions, which we're giving the variable w as a function of x. So w is the function variable. And units of distributed loads are typically given in newtons per meter, which you can see here, or pounds per feet if you're in English units. Those are typical. There are other units that you might see, right? So kilonewtons per millimeter or something, some variation of this would be common. And we saw a couple of different examples of these line loads to start. So one that is probably most common is the constant line load. So the loading function W is just equal to a constant C. Here we see three examples of three separate line loads. Here, this one is 6 kilonewtons per meter. This one here is 9 kilonewtons per meter. This one here is 3 kilonewtons per meter. And they're acting over various lengths. This first acting over 1.5, the second acting over 3, and the last acting over 1.5 meters, right? So those are constant line loads. You may see a linear distribution. So here, this is W equals 160x newtons per meter. So this is a linear function, right? Varying with the dimension x, where x is kind of starting from the left-hand side and moving to the right. It's a one-dimensional coordinate system. And it shows a peak value here of 1440 newtons per meter. That is what the line load is at the maximum length of x equals 9 meters. They put that in there for reference. You could calculate that yourself given the linear distribution on there already. You can maybe have, in some situations, some really crazy type of loading function. On the far right here, we're showing a polynomial distribution. Here, W is 2.5x to the third. So a bit of a crazy one, but the way that we analyze these and go about figuring out how to create an equivalent force for this distribution is the same, no matter whether we have constant, linear, polynomial, sinusoidal, whatever, it doesn't really matter. All right, so it's just a general polynomial loading that you might see kind of in math language in your math class, but the strategies will generally be the same, right? So we're talking about how do we analyze these? And when we're converting them, we need to convert them from the distributed line load that you see in 2D, we're only going to do 2D in this class, to an equivalent force. And we call this equivalent force, I label it as FEQ, so force equivalent. And the question is, what is the magnitude of that force? And where do we locate it so that it has an equivalent sort of static determinacy that we see with the distributed load? So we sort of talked about this on Friday, but the magnitude of this equivalent force that we want to use and generate in our figures is going to be equal to the area under the curve of the loading function. So here's our loading function, Wx, and depending on the domain we're interested in analyzing, some initial x position, some final x position, we're integrating from initial position to final position, and the area under the curve is just the integral of this loading loading function, Wx. So that's pretty straight ahead. Um, Simple calculus there. Most of the time we're dealing with constants or linear functions, so these integrals are going to be pretty easy. Next is the location, which is a little bit more difficult, but the location of the equivalent force to replace the distributed load is going to be equivalent to the centroid of the distribution of the distributed load. So mathematically speaking, we would label it in this way, x bar, and this is a fraction here where the numerator is the integral from initial to final position of x wx dx, and the denominator there, the integral from initial position to final position, integrating wx dx here. So this is very mathy, I understand, like these integrals here that we're looking at. I think it's best, and where we're going to start now today with this lecture, is looking at some very common loading functions, talking about how we can translate them and make new free body diagrams that use those equivalent loads. All right, so I'm going to show some very simple ones first. And the first that we're going to start off with is your simple constant loading function. So example number one is a constant loading function. All right, so we'll keep it general. And let's say we have some beam, just generally looks like this. And let's say it's simply supported. So a pin on the left-hand side here and a roller on the right-hand side. And a constant loading function is one that just looks like something like this. Right? And it's just Wx is a constant. So we'll just call it capital C. In this case, the equivalent force that you can use to represent this, by the way, this has some length L. The magnitude of the equivalent force is just going to be the area under the curve of this loading function. Well, this loading function is just a rectangle, right? So we can see this here. This shape is the shape of a rectangle. So the area of this rectangle is just the length times the height. So in this case, we're going to have C times L. That's the magnitude. And then the location, we label as X bar. It's the centroid of the rectangle. Well, rectangle centroids, or the center of the rectangle, is pretty easy to understand. We could call this centroid. And so we can show that X bar is in this location, which is L on 2. I think that's pretty straight ahead, right? So here, this would be located at L2, and that's where the location is. Pretty simple. We can maybe look at a numerical example if that's helpful to people. So I'm going to bring that same example that we were just looking at a second ago. I'm going to bring that in here, and we can look at this a little bit more clearly. So let's say I wanted to convert this example here that has distributed loads on it to one that has equivalent point loads. So I will sketch my beam. I will put in the appropriate boundary conditions. There's A, which is a pin, and B, which is a roller. And let's look at each of these individually. So here we have 6 kilonewton meters. Let's call this, W equals C1. So maybe we call this W1 equals C1. Here's this guy. This is W2 equals some constant 2, which here is 9 kilonewtons per meter. And then we have this guy here, W3. This is, let's call it C3, which is 3 kilonewtons per meter. I'll just label it as 3. So we're going to look at each of these individually and replace each of them individually with their own individual equivalent force. Okay, so for the first distribution, this acts over 1.5 meters, and it's 6 kilonewton meters. So our equivalent force is going to be located in the center of this distribution. So maybe we call this FEQ number 1. And this is equal to the area that this rectangle creates. So this rectangle here is the one I'm looking at. And it's just, length times height. So the length here is 1.5 meters. The height is 6 kilonewtons per meter. So this here is going to be 9 kilonewtons. pretty straight ahead. And we're going to locate this at the centroid of this distribution, which, okay, here this is 1.5 meters. So the centroid of this particular rectangle is going to be half that length, or 0.75 meters. So straight away here, we can just go 0.75 meters. So that's for distribution number one. We can go through the same process for the others. I'm going to speed up here a little bit. I think, we get generally the idea. The second distribution, this is 9 kilonewtons per meter, and it's acting over 3 meters. So this is going to be 27 kilonewtons. That's for equivalent force number two. That here will act, if we're taking a look at this, it's going to be at half of the length of this 3 meters. So this 3 meters here. The centroid of this guy is here. So it's going to be 1.5 meters plus half of 3, which will be 3 meters from the left-hand side. That's where that's located. And we can do the last one. The last distribution, I have 3 kilonewtons acting over 1.5 meters. So 3 times 1.5, that's 4.5. And it acts at the center of this distribution. So that's 0.75 meters. It's half of that length. And if I want to look at it from the left-hand side of the beam, which is probably appropriate, I'm going to have 1.5 plus 3, which is 4.5, plus 0.75 is 5.25. Locate that guy. Okay, so this is now statically equivalent. Both of these images, you can analyze them. The one on the right is pretty easy to analyze now with your free body diagram techniques, equilibrium techniques. We just have singular point loads, which we're probably much more comfortable with. All right, so that's a simple constant loading function, Wx equals c. The next, getting a little bit more tricky now, is a linear distribution. We can look at that with a bit more detail. So with a linear loading distribution, we could have two possibilities. That is that our loading function Wx starts at 0, meaning we have some mx. Typically you'd have a plus b here, but starting at 0. So a sketch of that is going to look a bit like this. Okay, so this is W equals mx, a linear function that starts at 0. So that's that. And the other possibility, if we label this as number 1, and the second possibility is that it does not start at 0. It's probably a more common occurrence. In this case, b does not equal 0. And this is a trapezoidal distribution. So this is triangular, I think pretty clearly to see. And if b does not equal 0, then we have a trapezoidal distribution. Okay, so if we're not starting at 0, it's going to look a bit like this. Okay, so it's a linear function, it's just offset slightly. Okay, Now, these two cases are actually kind of, they're quite different, right? Area of a triangle, replacing this guy with an equivalent force is pretty straight ahead. The area of a triangle, 1/2 base times height, pretty easy. The centroidal location of a triangle is 1/3 away from the larger side. That's pretty easy. Trapezoidal is much more difficult to handle. So we're going to start off looking at the first here, which is a linear distribution that starts at 0. And then we will talk about how to handle the trapezoidal distribution in just a moment. Okay, so first, a case where b is equal to 0. So let's do a sketch. And we'll label this and then sort of define it generally, and then we'll look at one quick example. Again, here's Wx equals mx, just a general linear function. M is your slope. Okay. And let's say this beam has a length of L. And my equivalent force is 1/2 base times height, since it's a triangular distribution. So it's 1/2 of base, which is L, times height. We're going to need to define our height here then now as some variable. Let's call it W max. In this case, this is just going to be M times L. But we'll just say this is L times W max. Okay, so 1/2 base times height. A lot of times that W max is given, but sometimes it's not. So there you go. This is the magnitude. And we can also look at position. X bar here is our position. It's our centroidal location. For a triangle, the centroidal position is 1/3 of the way from the larger side. So in this case, it's actually going to be 2/3 L. So 1/3 of the way from the larger side, that's going to be maybe about here. And that's true and standard for triangles generally. Okay, so here's my position. Let's look at an example with some numbers. I'm going to need to pause for just a second. The nurses came in.